are just reading in the data from the Excel file every time, it's going to take, depending on your computer, like 30 seconds or so for it to load in each time. So that's not what you want it to do. You want to read in the Excel spreadsheet file, export out using the save command to a .mat file, and then comment out the line that used to import from Excel and just import from the native format. It makes it so that the code runs immediately. There's no wait time at all. If you're not doing that, you're not really practicing what the lab is on, the new topic that the lab is on, which is importing and exporting data. So what we learned in this topic is that you can either use the native format, which is the .mat file, and the advantage of it is that when you load or save using the .mat format, your variable names come in and out automatically. It's really easy to use, it's really fast to use, and it also helps you start to understand the difference between a data file and an executable file, so a .mat file and a .m file. The alternative is that it can read in, MATLAB can read in any format of a file. So there's a bunch of non-native formats. We're only really focusing on two in this class, which are text files and Excel files, because they're the most commonly used in engineering. And so there's several different export-import commands. So for text file, there's DLM read and DLM write, but there's probably 5 other options. So you have to kind of check every time which one works best. And then the XLS read and XLS write for Excel spreadsheets. Can anyone, does anyone know why we look at both non-native and native? Like, why am I just not using native all the time? Yes, because there's stuff outside of this class that exists in the world. So barely ever will you have data in the native format. It's almost always in some other format. So if you can get it in the format of MATLAB, great. That's the first choice. But usually you can't. So it's good to know that there's all these other ways to read in files. And I'll just remind you, if you need to look up any of these commands, you just Google or search the help for a MATLAB file format or a MATLAB supported file format, something like that, and you'll see this table. It's very easy to find, and it summarizes everything. You don't have to remember any of it. All of it has different syntax for inputs and outputs, so it's not worth memorizing. It's just worth knowing how to do it, okay? Do you guys have any questions? Yeah?
Will something this exact show up on an exam? Like, how do you read an Excel sheet?
Like you should know the import-export commands from MAT files, Excel files, and text files, like one of them, but that's it. You shouldn't know anything specific or tricky about any of those things, but you should especially be able to read, if you're reading code, you should be able to read any of those. Any other questions? But just like if you think about it, it's really hard to test on this. It's really hard to test on reading and writing files because you have to have the file. Okay, on it. But it was really general. Okay, so we're going to do the next topic now. This is like one of my favorite topics because I am a modeler. My research focus is in computational fluid dynamics, so pretty much all I do is solve partial differential equations on computers over and over again. That's what I do. So this is like step A of what I do. So I really, really like this topic. It's also a good prep for 303. Is this an autofocus on? 303 basically takes this and does a bunch of, in 303 you're mainly solving differential equations using MATLAB. That's the most, that's probably the most frequent topic in the course. So this is definitely the prereq for that, this topic. So we're going to do a couple different things today with integration and differentiation. Because there's a lot of different tools in MATLAB that can help with this. So the first one is there's a toolbox. This is the only toolbox we use in the class, and it's called the symbolic toolbox. And I'm going to show you how to use it because it's really useful for checking your work. It's also useful if you're still in any of the math classes. But it can do symbolic, algebraic, and it could basically do symbolic, algebra, and calculus. So if you've ever used Mathematica, it's basically the same as Mathematica, but there's not a GUI. So it's all code based. So there's no user interface to like push buttons, but it does all the same things. So I'm going to just show you how to use that. You're going to do it a little bit on your pre-lab. And then after I show you that, we're going to do the derivative and the integral in its numeric form. So I'm going to start with numeric derivatives, which are called numerical finite differences. And then I'll end with integration. So these two are numerical methods. So they're approximations of any of the calculus that you've done in your math classes. So we never solve any real engineering problem analytically. It's always solved on the computer. So you have to be able to translate all those analytic expressions you have for derivatives and integrals into something the computer can solve for, and that's what we're going to do today. This symbolic toolbox is not numerical, it's symbolic. So if you're trying to find the derivative of sine, you can put it into MATLAB and it will tell you its cosine. And so it's a symbolic feature. It's really just used for academic use. But it's nice for comparison. If you're trying to do something numerically, you can use it to see if it's right, basically. So let's start with the symbolic toolbox. No. Differentiation translates to differences numerically, so we call them finite differences. Yeah, I'll explain it more. So the syntax for the symbolic toolbox, I'm going to write a few things down and then I'll just show it to you in MATLAB, is that it's a toolbox and it's one of the only that doesn't pop up with like a little window that you can push buttons on. So it's all just command window. Everything's executed in the command window. So the first thing you do is you type SYMS in the command window, and that means that you are going to define everything behind it as a symbolic variable. So if I do SYMX, it makes X symbolic. So what that means is that X can't hold a variable, or sorry, it can't hold a number. It is just a symbolic variable that you can make other functions depend on. So for example, if you type f equals sine of x, it's going to make f symbolically depend on x. So I'll just show you some of the rest of it. So SYMSX makes X symbolic, so when you look in your workspace after you execute that command, you can see that it's listed as SYM, and then you can define functions based off of that. It's also symbolic. And then there's all of these functions, and you can look through the help under the symbolic toolbox to see all of them, but there's something called diff, which takes the derivative. DIFF is the function. And then there's something called INT that takes the integral. And then there's a lot of optional inputs. So you can just put the thing you want to take the derivative of, so you can just put f, and it will take the derivative of the first or only symbolic variable that exists. Or if you're starting to do multivariable calculus or partials or anything like that, then you can have things have more than one variable, and then you can indicate what you want to take the derivative to. All of you are actually in very different maths. We have freshmen through seniors in this class, so it's actually really confusing. So if you're earlier on in your math, you've probably never heard of this, but there's just, you can just take the derivative of anything with respect to anything. The integral is the same way. You can also add like a number to plug in for the, oh wait, not for the derivative, for the integral. So you can put bounds in on your integral. So let's say you wanted to go from, integrate from 0 to 1, and then it will actually do the calculation for you too. It usually keeps it as, it doesn't give you out decimals unless you ask for it, and I believe, this could be wrong, I don't remember. Yeah, VPA converts whatever you put in into like the actual number that it is. It's sometimes useful if you're just looking for the number. And it's like, it could go on and on. Like there's so many things. If you're ever just doing algebra, like really messy algebra, you can type it out. And there's these functions called simplify or simple or expand that can do the algebra for you too. So I just like to just show you this, and you can take it wherever you want. But it's there, and you'll just do a few things in the pre-lab, okay? But just keep in mind that this is not a numerical thing. This is just a toolbox that does symbolic math, okay? Just like Mathematica. For some reason, it often gets, it gets very confusing for people. That gets mixed up. I forgot to do the recording this, so just let me move it over really quick. Sorry, I don't know, it's not working. Didn't this happen last time? There we go. Okay, so that's the symbolic stuff. So now let's move on to number 2, which is introducing the numerical equivalence of a derivative, and then we'll do the integral. So before I start, let me just distinguish between discrete and continuous mathematical analysis. So the idea is that most of the math that you've looked at is dealing with continuous functions and variables. So you are looking at analytic expressions like polynomials or trig functions, and you're just taught to remember what those derivatives are and just how it basically works, what a derivative is with respect to an original function and things like that. When you start working on a computer, you always have to discretize, which means take analytic expressions and just look at specific points and then use smart translations to make the equivalent expressions with discrete math. So here you're always looking at discrete, you're always looking at continuous. And the idea is that calculus is this very, it's very beautiful human language, but computers cannot do calculus. They can't do derivatives and integrals. That's not something a computer can do. A computer can only think in zeros and ones, binaries, right? That's if you go all the way down. So the idea that what we do when we start discretizing calculus is that we want to turn calculus into algebra, because computers are great at algebra. Computers can add and subtract very, very fast. And so derivatives become subtraction and integrals become sums. And it's literally that simple. That's all numerical methods are. And there's just a bunch of different ways to do it. So we're going to go all the way back to the fundamental theorem of calculus for finite differentiation. You guys remember that? And we're going to think about what is a derivative and can we make it algebra? So the fundamental theorem of calculus is actually not that complicated. It just is saying that if you have a point x and you go over h away from that point, so x plus h, and you look at the function value at x and then the function value at x plus h, the fundamental theorem of calculus says that if you take the slope, so the rise over the run, delta y over delta x, and you take the limit of that as that distance between the 2 points approaches 0, so that those distance gets closer and closer and closer together, that exactly approaches the derivative. That's all the theorem says. And if you're a math person, you know that that's not exactly true, but you know what I mean? That's good enough. So we're going to use that theorem to basically do the same thing with discrete points. So if we have a set of points, so let's say we have some data at discrete points, and we want to know what the derivative of the data is. So let's just imagine that you were doing like a physics experiment, since all of you have taken physics, probably, and you were collecting distances at certain times. You were just like measuring distances at certain times, and you have, at time 1, it had gone 3 feet. At time 2, it had gone to 6 feet. At time 3, it had gone to 7 feet. Imagine what this data is, and you wanted to know the velocity of the car that you were measuring in the experiment, something like that. How would you do it? Well, you would just difference the two distances next to each other and divide them by however the distance of time was, right? So that's all finite difference is, but we write it in a way that makes it easy to generally write. So we use an I index. So I'm just going to call one point xi, and then the point on the right xi plus 1. The I just means that it could be any point, and the I plus 1 means it's the point to that point's right. So I could call any point the I point. And that point is also going to have an f value, whatever it is, the distance, for example, in the example I gave you, that corresponds with that x location. And same with the I point. So a finite difference would say that the slope at point I equals the point in front of it minus the point itself divided by the difference in x's. And what you'll see in a lot of notation, including in the book, is that instead of writing xi plus 1 minus xi, they just call that distance h, and h is called the spacing. So in modeling, which is, you're going to take a lot of different modeling classes, h is referred to as the mesh size. So it's this distance between points. for most cases, it's constant throughout the domain. It's the same distance because that's usually how like instrumentation works or anything as it collects it at evenly spaced points. And so then you can just call this at h. You don't have to index it with I because it's the same between every 2 points. But generally you can keep it indexed with I and let it change. In the lab that you're working on, you're going to be taking the derivative of Tour de France data, and it was taken using some instrumentation that took it at every, I think it took it every minute, but it's the same. So your h is the same for every 2 points. So you don't need to necessarily keep track of it within the loop. So how does this derivative get better? What makes the derivative more accurate using this approximation? Yes, the closer the points are, the more accurate it is. So depending on the application, if you are only given so many points, that's all you can do. That's the best you can do. But a lot of times we do this in modeling and we refine our grids enough so that this is accurate enough for the physics that we're trying to solve. So let's just look at how you would do this algorithm. So like all things, you can do this using a loop notation or using vector notation. So I'll show it with a loop. So let's say I have some data. I have an x that goes from 1 to 10. And then I'm just going to create an f data based off of the sine function just so I have some, but it could be anything. And we're going to, we see that this is evenly spaced, right? So I'm just going to define my h as the distance between the first 2 points because I know it's evenly spaced, which is what you can do in your lab as well. So I'm just going to set up a loop that runs through every point and calculates the derivative. So I'm going to go from 1 to the length of x. And at every I location, I'm going to calculate the derivative at that location. So keep in mind that when you're doing derivatives of data, you're going to always have a derivative for every data point. When you're doing integrals of data, remember integral is the area under the curve, so you get one number after doing an integral. So we're going to call the derivative df, and I'm going to index it with I because I want to calculate a derivative at every I point. And then I'm just going to apply this equation that I already wrote in index form. So I'm just going to access the point in front of it, subtract the point itself, and divide it by the h variable that I already defined. Does anyone see a problem with the code that I wrote? Yeah, I could write it more general with a general h, but for this one it's okay, right? Anything else?
Does your x have to be an array?
It is an array. 1 colon 10 is 1, 2, 3 all the way up to 10. No, with the colon you can leave them out. Yep.
On the final iteration, fi plus 1 is going to run over the end of the array.
Right. So if I equals length of x and then I try to access the length of x plus 1 element, that doesn't exist. So there'll be an error, right? So I can't take the derivative using this type of difference on the last point. It's not possible because there's no other point. So I can only go to length of x minus 1. And then on the last point, I have to do something else, right? I have to use some other derivative. So I can just define the derivative based off of the point in front of it on that last point. Does that make sense to everyone? Doesn't really matter which 2 points you use, you can choose. But on the last point, you're going to have to change the derivative. And I'll talk about that in a second. So that does all of the points except for the last point. And could anyone tell me how I could make this code faster? I can pre-allocate, that's right. So I can just set df equal to zeros that are the same size as x. So this is how you do it in a loop. So let me just show you how you can do the same thing in one line with vector notation. So instead of doing each one individually, and remember this is the whole point of MATLAB, this is why MATLAB is used, is because of the vectorization capabilities. This is going to take 9 times longer than doing it in vectorized form because it's going to do it one at a time, and this is going to do it all at once. So I'm going to define all the points in DF, except for the last one, all at the same time. And then I'm just going to apply that difference at once. So I need to shift over to the right. So that means I need to go and start at the second index and end at the last index. And that will be equivalent to the I plus 1. And then you can see that these i's match, they're unshifted, so it's the point that you're taking the derivative at. So I'm just going to go from 1 to n minus 1. So it's going to take and grab those 9 elements in each of those spots and subtract them all at the same time. And this is 9 times faster than the loop. And you don't have to pre-allocate because it's getting defined all at once, so it's not slow. So this is called vectorizing your code. So you can choose, you can do them either way.
Would you run through that vectorized? Use why you went from 2 to
You can actually think of it by just counting through. So just look at your loop. I equals 1. So you're going to define the first point based off of the second minus the first. So it's the first point and the second minus the first. And then if you go through and keep doing each one, you'll see that they all match up. It's doing a lot of things at once, so it's pretty complicated, but some people really prefer it because it's obviously way easier to program vectorized. It's just harder to find mistakes. So we just did something called a forward derivative or a forward finite difference. And that's because we defined the derivative using the point in front of it. But there's three kinds that I want you guys to be aware of, and you're going to use all 3 of them in your code. I want you to choose the best one to use at each point that you are calculating the derivative at. So a backwards difference is just the opposite. So you use the point itself and then the point behind it. So for example, on the end point, that's the only type of difference that you can use. And then, does anyone think of something better than either of those two? Use both, right? Use both points. So that's called a central. So a central finite difference is going to take the point in front of it and subtract off the point behind it. And what would you divide by if you were using 2 points? H or something else? 2H, yeah, you're going to have to do 2H because you're going over there's 2 mesh sizes in between the points. So in your code, when you have to do the derivative, you should be using central derivatives and all the middle points because central derivatives are better, they're more accurate, and then using forward and backwards just on the end points. Okay, so now we're going to talk about integrals, and first I'm just going to define an integral. I'm going to use this notation throughout. So I'm going to use I as the integral, and remember it's just a number, and it just stands for everything that you're integrating between your bounds. So I'm going to call the bounds A to B. So if you want me to draw it for you, let's say this is your function f of x, this is your A, and this is your B. Remember that the integral is just the area under the curve. So I is just whatever area that amounts to. So what you're going to do in your lab is you have, so it's a bike, just a biker, and you have their speed that they're traveling in the race. And if you integrate their speed over the time, you should be able to calculate the total distance of the race. And you can compare it to the actual distance. It's like stage 16 of the Tour de France, and you can see that you get the same thing basically. So that's just graphically what it looks like. When we do the numerical equivalent of that, numerical integrals are based off of the idea that you just need to approximate the area under the curve. So what are your options for that? So let's say that instead of having a continuous function like I just drew up there, you have some points, which is what you're going to have. You're going to have a bunch of velocity data. The idea is that you take the function values that were given and you just create some rectangles based off of those function heights. And you calculate all those rectangles and you just add them up. So you're going to have a bunch of different little integrals that we can just number with the place it is in the data. So here I have 6 different rectangles using this rough rectangle that I used. And the integral can be approximated by just summing all those little areas that I just drew out. So that's why derivatives are differences and integrals are sums, because you're just doing a bunch of summing of areas. And if you knew the velocity y value and you knew the distance of, or the spacing of time intervals that the data was collected, you can easily just calculate those rectangles, right? So in general, we write the numerical approximation as a sum of function values multiplied by widths or weights. So they're just rectangles usually, but you can make them better by doing trapezoids or more sophisticated approximations of those areas. So that's all a numerical integral is in general. And so all the different methods for integration, numerical integration, are just different ways of doing that, different ways of approximating the areas. So I'm going to show you the ones that I want you guys to use. So I think probably most of you have heard of most of these. I don't know when. Do you do this in calculus? Probably calculus, right? So the first one is just called the rectangular rule. You don't use it to actually, usually you don't use it to actually, I'm done talking about that. I was just going to bash a lot of things. I'm not going to do that. So, so it's either the left hand or the right hand rule. So the left hand rule is going to use the point on the left side of the rectangle, and then the right hand rule uses the point on the right. So the equation for the area calculation is really easy. You just take the spacing between the 2 points and multiply it by one of the 2 function values. So you don't have to necessarily distinguish it. Just when you program it, it's just which one that you grab. So it looks like this. If you want to do the left-hand rule, let's say you have 2 points and you're trying to approximate some function that looks something like that. The left-hand rule is what I'll show you, would approximate the integral like this. So the left-hand rule on this function is going to totally undershoot the integral, and then the right-hand rule would overshoot the integral. I think I'm just going to skip that one. I'm going to just show you trapezoidal rule. This is what you have to use in your lab. So if you have enough resolution, trapezoidal rule is usually the standard, because usually you have plenty of the resolution of the grid is usually enough in most applications to just use trapezoidal rule. You don't really need to use anything more sophisticated. So what trapezoidal rule does is it takes an average between the two function values and multiplies it by the spacing. So visually it looks like this. So it's a linear line between the two. And it actually takes a little bit of effort to actually show you that this is the same as the equation, so I'm not going to do that, but you can refer to the book for that. But the equation for it is that you just take the two function values, average them, and multiply by h of I. But just imagine like taking the triangle that's there and then the rest of the rectangle, and you can actually get to this equation. So these are some ways to approximate the area under the curve over one interval. So that's why it says up here, over a single interval. But we never would just take a bunch of data and take the first point and the last point, average them, and multiply by the width. You do it over every single point. So there's a bunch of these. So the trick to the code is to sum these over all the points. And unfortunately, if you look at any numerical methods class, they really only talk about, textbook or any reference, they really only talk about the equations over a single interval. And when you need to program it, you need to think of it over all of them. And so that's why I want to make sure that you see this. So the actual integral is the sum of all of them. So for example, for the rectangular rule, what you're going to program is a sum that goes from 1 to n minus 1, where n is the total number of points in your data set. And you have to do that because, remember, every rectangle needs 2 points, so you'll always have one less rectangle than you have number of points. So you're just going to take and multiply h of I times f of I. It depends a little bit on how you index, so be careful about that. But can anyone tell me which rule this is? Is this left-hand or right-hand rule? This is going to be left-hand rule because the first rectangle uses the first point, the second rectangle uses the second point, so that's always the left point. If I put I plus 1 here, f of I plus 1, then that would be the right-hand rule. So it's pretty easy to program the rectangular rule because it's just a sum of two things multiplied by each other. You guys are going to program the trapezoidal rule. And since you've already written a sum function, you can call the sum function that you've already written, or you can just add another loop, especially if you want practice on the sum algorithm. But the trapezoidal rule will look similar. It also is only using 2 points, so there'll always be one less trapezoid than there is number of points. So you're going to sum from I equals 1 to n minus 1, h of I over 2, f of I plus f of I plus 1. And what I'm going to kind of leave as an exercise for you is the challenge of trying to write this. You can write this in one line very easily, the trapezoidal rule, by vectorizing it and just accessing the right points. So what I want you to think about with the trapezoidal rule is how many times do you use each point? So the end points are only going to get used once in the sum, right? They only get used on the first trapezoid and the last trapezoid, but all the interior points are going to get used twice because they're getting used on 2 different areas. So you can actually generalize this to be very simple, and I encourage you to go for that. Do you guys have any questions? Okay, that's it. Thanks.